Okay. Okay, so the format of this cube gen, you take space. Well, the argument of cube gen is your form check file. So it tells from where the information is taken. The last argument is the name of the file where you want to dump this cube information about space distribution of the orbital. And the additional two parameters is letter O stands that you want O orbital. And MO stands for molecular orbital, equals and then number. Right? So when you hit it, it thinks a little bit. And then after it is done, if you, let me do immediately the 25 as well. And after it is done, if you list your files, you observe that there are files with extension cube, and they are a little more heavy than the original form check. So instead of encoding, the form check has encoded dense information telling like which atomic orbital has which percentage contributing to molecular orbital, right? Expansion coefficient, something like this. And cube is a literal map, three-dimensional map of this values of orbital. So one might want to open this file, right? And, it will be very easy to do in Gauss view. So you open Gauss view, open this file and deploy it, right? With a couple of mouse commands. Before we go there, I want to keep asking random questions. The wave, so this orbital, I, X, Y, Z, map, cube of numbers. But what is a standard way to visually represent orbitals for humans? You were already showing it, right? Clouds. What is a cloud? Not in the sense of storing information, but in the sense of obsolete 50 years ago textbooks in chemistry when one draws S, P, D orbitals. They all draw these clouds, right? What is it? I'm asking something really naive and simple from common sense thinking. So they look like pumped balloons of different shapes. And the function is three-dimensional, but balloon is, you do not see what is inside. You do not see what is outside. You see on the surface. So it converts a three-dimensional map into a surface. So how the surfaces are constructed? So this was three-dimensional, and surface to some extent it is two-dimensional. Well, it is a mathematically complicated object. It's not flat, but if you are sitting on surface, you can go left, right, forward, backwards, but you cannot jump up or down. Right? So in some sense, it is two-dimensional with non-trivial topology. Yes. So you project three-dimensional object into two-dimensional. with which algorithm? How these balloons are coming up? If there will be no computational chemistry and you guys would design it today, and you need to plot orbitals, how would you do it?
Would be based on probability.
Probability. Yes. On the value, you can make it absolute value square or keep the value of probability.
Yeah.
So, did you hear what Vijay told? Value of probability. So, if probability is bigger than a threshold, then you cover this little area of space by solid skin of balloon. If the value is smaller, you do nothing. It is a free space. Excellent idea. I do not have this strong intellectual strength, so I will do it in one dimension. I will project from one-dimensional function into zero-dimensional point. So suppose I have some one-dimensional orbital, phi of x, right? And I set up a threshold, psi t. So for all values where wave function is bigger than threshold, I will tell here is the limit of my balloon. So my balloon will have this size. Everything outside I will forget about it. Right? So here we project from one-dimensional to zero-dimensional, just from one point. But if you do the same for surface, like I do not have much fantasy to do complicated shape, but if it is, it will be just one hue, right? Two-dimensional, x and y, and we set up the threshold value. So we will dissect. We'll dissect this hump by a line where it has the same height.
I have a green marker if you want.
Oh yes, thank you so much.
Yeah.
So this is dissecting surface, which identify the threshold value. So everything above will be considered as the area where orbital allowed to exist. Everything below will be considered as nothing, empty. And here we will draw one-dimensional circle. And if you look from above, it will be like circular or whatever, circle with field circle, round orbital. Right? But depending if we select the higher threshold, the radius of this circle will be smaller. If we select lower threshold, the area will be larger. So we are going from 2-dimension to 1-dimension. And I do not have drawing skills and imagination to do in 3D, but you can follow basic idea. If you do same thing for 3-dimensional, the threshold will project a 3-dimensional map onto 2-dimensional non-trivial shapes. And therefore, the surfaces are called iso surfaces. Iso means equal. So at each point on this surface, the value of absolute value of wave function has the same value, iso value. Make sense? Okay, it was too much of mumbling, but actual practical thing is 30 seconds. So, yes.
So then, when you choose your ISO value, then you take every element in the cube file squares it and compares it to the ISO value that you set?
Or absolute value, not squared, but just absolute value. So that if there are negatives, they are also included. If you would discuss the density without plus and minus, yes.
So just absolute value.
So if I am in Gaussian, open cube file. So make sure that in the file type you select this cube, which means it is three-dimensional map. And after you open, you will see nothing. You will see just your model, but you shouldn't panic. So nothing is broken. It is normal because you just downloaded the file into your GUI. So the next step, orbital is to some sense is a result. So you go to menu results and select surfaces contours. So you see this numbers 80, 80, 80. It is number of grid points along each dimension. So it is array of data with cube with 80 points along each dimension. 8 times 8. Too complicated. 8 it is a 2 to the power 3. 8 times 8 times 8 it is 2 to the power 9. 8 to the power 10 is 1024. So 8 to the power 9 is 512. So it is 512 and 3 zeros. So it's 500,000 grid points just for one orbital. So if you want to do 100 orbitals, think ahead, if you really need them. So before you do something, you select the value of ISO value for new surfaces. See, you have this ISO value for ISO surfaces. And if you like, you can just keep the default version and do surface action, new surface. So you may realize that the image is, please do it. Please do it, and I will make a walk around. Oh, let me wait somewhere. CHEM. Space. Letter O. Letter M. O equals something you like. Space. Your file .fchk. Space. Your file that your creative name for orbital.cube. Yes, exactly.
Everybody's just now.
Right. Okay. Nope, it's not done yet.
It is a different form.
They're running like what thing did I show you those?
Mm-hmm.
Just make sure to get those together.
Yeah. It's like 20 minutes.
Okay.
Yeah.
There we go. It doesn't show it.
Yeah. Mine. It just killed itself.
Usually when I get frustrated.
Can you just
Yeah. I mean, it just kind of quit.
I was almost gonna say I killed myself, but then I realized that was really bad.
Yeah.
I was gonna be like, oh, I also do that. I thought about what I was doing.
Yeah. Good call.
Did I tell you Dr. Rogers said this?
Success?
Did I tell you that?
No.
Just
We were in our review session for one of our tests.
So I tried to.
He was taking like an extra day to grade the homework away
check
from him like 2 days before. Because he was always like, oh, you should homework back right away. He's like, if I don't get your homework back by tomorrow, like during class, I'm skipping this. And everyone was just like,
What?
please take your time.
Yeah.
I was like, it's golden. You're fine.
In condensed matter physics, Kong said that once too.
Really?
Yeah. When he was telling us that we should all be able to define reciprocal lattice.
If you aren't all able to define reciprocal lattices, you can do that. Oh God. That's even worse because that's putting the stress on you.
Right. It was a homework question. Good.
Number of highest orbital rules than each planet. The new occasional consent.
I finished 16 simulations in about 2 minutes.
You used to do it?
No. These take more than 2 minutes just to even create. I'm so hungry. Yeah. I ate my sandwich around like
I packed myself some snacks. Oh, that's fine.
true. I have a granola bar. Glad I ate a cupcake earlier though.
Alpha and beta, like alpha and beta states.
Mm-hmm.
The open shell.
didn't discuss scientific work, just procedure.
So everyone got the orbitals, right? So if your aesthetic feeling suffers, if you think that it is too ugly and you want to, if it just occupies all space and you are not happy with visual appearance, what you can do, like hide or remove surface and increase the ISO value maybe 4 times and then redraw orbital. So I changed this number from 0.02 to 0.08, 4 times bigger, and redraw the orbital. Do you recognize this symbol and what does it mean? From your everlasting chemical intuition.
Looks like SP3 or SP2 hybridization. It looks kind of like P, but a little bit S in there.
How many, if it is a flower, how many petals does it have?
4.
Which orbitals?
Oh, so like
D orbital?
Yes, it's just a d orbital.
Okay.
Yeah.
So transition metals are those with d orbitals on the top, right? If you make this Aufbau, which means populating hydrogen-like atom with electrons, and you stop somewhere, if you stop in the middle of populating the element with d electrons, d orbitals, it will be transition metal. So this was LUMO, right? Number 25.
Oh, okay.
Which figure are you getting if you draw highest occupied, HOMO?
What was the question?
So if we would write a mini paper on this assignment, our conclusion was that LUMO orbital exhibits D character centered on the titanium metal, right? If you want second conclusion, the highest occupied, which character does it have? And where is it localized?
Probably P character on oxygen or something.
So we have a educated hypothesis that if you draw by Braden, if you draw molecular orbital number 24, highest occupied, it will be p orbitals. It's just 2 petals localized on oxygens. Let's check this hypothesis. And if you have already drawn, if you did number 24, you already have it. Right?
Yeah.
Those are
This is my
pure.
It's definitely not
Yes.
D orbital.
If you
Oh, it's a DZ squared. I just need to go back and study Griffiths because you know how when we were doing the hydrogen atom, we had those nice pictures. Yeah.
So you should read my inorganic. I say this all the time.
Yeah.
Read my inorganic. It's so much physics in there. Actually, it's
Okay.
not as much chemistry. Kind of approaching it from physics.
So those
Good.
I mean, it's not for physicists, so it's like geared toward chemists, like liquid and stuff.
Yeah.
But it's really physics, like basics.
Let me suggest that if you are getting some images, you may print screen and put it in your PowerPoint because the next homework will be printing orbitals for all models that you have. So it will be contribution to your homework. Yes?
So if I wanted to compare two orbitals, say the HOMO and LUMO, or the HOMO of 2 different species, and I want to make sure that the grid points, I would have to make sure that the grid points are all the same number of grid points.
Mhm.
Are you familiar with how to do that? How to specify the alignment?
Let's try to put like each 100 and see what would happen. I don't remember exact No, I would not tell it from the top of the head, but there should be keyword specifying number of grid points along each direction.
And so, how does it automatically choose? Do you know? How does it automatically choose the default?
To match some threshold for continuity of these functions. So see for the highest occupied, because we were not, I don't know about you, I was not putting too much attention to optimizing. It can be not equal on each of oxygens, but it has this standard shape of p orbitals. And the observation that we have made right now has chemical meaning. You can already analyze situation and in the following way. So the metals are typically reducing agents. They release electrons, they donate electrons somewhere, right? And oxygen is oxidizing agent. It pulls electrons. Therefore, oxygen pulls. Each oxygen pulls electrons from titanium. From titanium, so all occupied electrons will be, they were stolen by oxygens from titanium, therefore they are on the oxygen, and the titanium orbitals are empty because oxygen removed electrons from titanium. So if you look on the empty orbital, so LUMO is nothing but empty. It's unoccupied. It is localized on titanium, and it has this D character, D shape. So if you can convert your titanium hydroxide results into these orbitals, then you're fine. We spent an hour on this. And I know that you did it before, but if you forget about it, here is the main command, QubeJet. So please practice, and I will prepare next demonstration for a couple of minutes. By now, I consider that you all know how to do orbitals, and you know how to control their shapes by changing the ISO value. And next thing we'll discuss is the open shell configurations and orbitals for open shells.
Yeah, much better. This is such a good structure.
But that's not the
No, I ran
Oh.
I thought that's what you're supposed to do. True.
Structures that aren't 1500
Okay, so what are we going to do? We are going to talk about open shell configurations. And what I'm going to show right now will deal with the little challenge that you may have seen in the a little challenge that you may have seen in the homework, where you were offered to find density of states for complex with manganese. If you did try it, you've got some error message or something strange. Right? No? So, right now I'm forgetting about density of states for a minute and just doing this orbital 24, orbital 25 for the titanium hydroxide, titanium OH4. If you would plot orbitals number 26, 27, 28, 29, all this 1, 2, 3, 4, 5 orbitals will have D shapes. You'll see 5D orbitals, all unoccupied. And you know that up and down, up and down, up and down. So you do have all occupied orbitals have 2 electrons. 2 electrons means closed shell. But what if you place your hydroxide in the acidic environment? That will pull 1 electron out of it. So we remove electron, and we do have an orbital half occupied, or occupied with 1 electron. Are we allowed to do our standard practice, our standard procedures for such open shell things? No, we don't, and Gaussian has a proof that forbids us to do so. It will fix our errors, even if you try, or if you do not resist, it will fix this error. So the idea is that right now we were thinking that orbital is like a step on the ladder, where 1 person or 2 persons can step on, right? But in fact, the ladders, the steps for electrons with spin up and electrons with spin down are different. They often coincide if it is a closed shell. But more correct picture would be to have set of orbitals for spins up and spins down. Nothing. So same molecule, but orbitals are separate for spin up and spin down. So here we have epsilon I comma up, epsilon I comma down. Right? So different energies of orbitals, and later you will see it could be different shapes of orbitals for different spins. If they are in the closed shell situation, as most stable chemicals, we do not need to think into this direction. We can assume that orbitals are the same for alpha and beta, for up and down. But if we remove 1 electron, what happens? The energy of this orbital can float up, or maybe it float down this one, so they may reorganize substantially. There will be specific components in energetics that will affect differently, spins up and spins down. And the error can be so big that without this thing, calculation will not go through. Therefore, if you assume that you may need such situation in your command line of the task in your input file, where you have Hartree-Fock, HF, you need to add the letter U, UHF. And whatever you do, just add letter U. U means unrestricted. So energies of orbitals for up and down are not restricted to be the same. unrestricted. Okay.